The speaker, Mohammed, is a memory system architect at NVIDIA. He earned his PhD from Carnegie Mellon under the guidance of Professor Philip Gibbons. And his research has been on intersection of robotics and computer architecture. So, the stage is yours.
Hi everyone, I'm Mohammed. I'm going to present Tartan, Microarchitecting a Robotic Processor. As mentioned, I'm currently affiliated with NVIDIA, but this work was done while I was at Carnegie Mellon University. Here is the rundown for the talk. Tartan is a domain-specific processor. I will start by its architecture, to explain its architecture, and then the methodology of this work, which includes extensive profiling of robotics workloads and finding execution bottlenecks in them. And finally, I will introduce the architectural techniques that we use in the design of this processor, which include, in this talk, I will go over 2 of them, oriented vectorization and approximate acceleration, and more techniques are in the paper. So on this spectrum of generality performance for the computation robotics, currently we have on one end general purpose CPUs like Intel Core i5, which is extensively used in the current market for different robotic applications. And on the other end, we have a variety of research proposals and artifacts that are about ASIC hardware accelerators, including RACOD, our own prior work, which target a specific application and try to execute it with the highest possible performance. This work, Tartan, targets the middle ground. So it proposes a domain-specific processor, which is a CPU essentially. So it is general enough to run a variety of workloads. But in the meantime, its architecture is specialized not just for one specific application, but for a domain of applications. Examples of these domain-specific processors are the Shah's Anton processor, which is used for dynamic molecular simulation, Cisco's Silicon One, specialized for networking, and so many other examples. Tartan is a processor whose architecture is specialized for robotics workloads, and it includes both computational units and memory extensions to excel robotic workloads. Our methodology involves modeling a baseline processor in a simulation framework. For this purpose, we use Intel Core i7, which is the processor used in NASA's Valkyrie robot. It includes 4 cores, 8 megabyte last level cache. And then we choose to use RoWild as our workloads. RoWild is a recent workload suite. It targets different robotic applications. It models their end-to-end functionality, the entire software pipeline, and it models robots with different missions. Their name suggests those missions, like Delibot performs delivery, Petrobot perform patrolling, and so forth. We start this work by identifying the bottlenecks in their execution, the execution of different workloads. As we see, different workloads are bottlenecked by different functions. For example, Delibot is bottlenecked by raycasting, Petrobot is bottlenecked by network inference, and so forth. So our purpose is to accelerate these bottlenecks in the architecture of Tartan. The first technique that we introduce is oriented vectorization. Tartan extends CPUs, current CPUs vectorization unit to handle slanted line address patterns. These patterns are numerous in many dominant kernels like raycasting and collision detection. For example, raycasting is the process of aligning sensory data with robot's belief, and it involves checking robot's belief map in different cells nearby each other, but not axis aligned. So we have traversals that are that correspond to different rays, and the directions in the computation correspond to the direction of the rays. Similar happens in collision detection. The problem is current vectorization engines cannot handle this type of computation, even though the computation is the same on every of these cells, and these cells are nearby addresses. So traditional vector instructions are like this. We have a general purpose register and the base address to which, from which the data is loaded, Tartan adds this new instruction, oriented move. It is similar to the traditional instruction, so it has the same base address, but in addition to that, it has another operand which encodes the orientation in a scalar register. And ZMM is a destination register, general purpose vector register. And once the data is loaded, it uses vector ALU similar to other vector instructions. So the main difference between this vector instruction and its execution and traditional instructions is its address generation. Here we have to generate addresses explicitly. For this purpose, we use this circuit. The two operands, the origin address and the orientation, are weight summed in this manner. Their fractional part are omitted, and the addresses enter load queue. The main argument here is that these operations anyway would have been done in software without this instruction, but this instruction performs all these operations in parallel in hardware, which contributes to the speed up results that I will present. So the results of this technique alone for 12 the robots, Delibot and Caribot, that are bottlenecked by raycasting and collision detection shows that we have around 1.6 to 1.7x speed up in these bottlenecks operations. The next technique is approximate acceleration. This is motivated by the observation that many robotic applications allow for some level of approximation. For example, consider a vacuum robot. The ideal scenario is that the vacuum robot cleans every spot in a floor, but in reality, missing a spot or two doesn't change the cleaning outcome that much. So it means that there is some leniency in its execution. So Tartan proposes to accelerate these operations. To this purpose, Tartan replaces costly approximable computations with a neural network, and the neural network in execution runs on a hardware accelerator dedicated for this purpose. So this is the procedure for a costly approximable function. We provide some sample input and get the output, and using these input-output pairs, we train a neural network. And this training operation is done offline. And in runtime, this neural network, when it is invoked, it is simply offloaded to the accelerator. The accelerator, MPU, is a stereotype neural accelerator. It has several processing elements, each with a specialized hardware like multiply, accumulate, and sigmoid activation implemented as a lookup table to accelerate these operations. And this highly parallel hardware is expected to run neural models much faster than the original code would have run on the CPU. The applications of this technique are computationally intensive functions that can be replaced by an efficient neural network. And efficient here refers to computation, meaning that the network shouldn't be too large to outweigh the benefits of hardware acceleration, and it should be accurate enough in replicating the output of the target function. So the results for this technique for 2 of the robots, HomeBot and FlyBot. In HomeBot, we have T-prediction, which is a computationally expensive operation for predicting the transformation matrix of a robot in order to understand its translation or rotation in the wild. And in FlyBot, we have heuristic cost calculation, which is, again, another computationally intensive operation, including it includes data integration, aerodynamic calculation, and so forth for providing an estimate cost. But this operation itself is a very computationally intensive one. So we replace these operations with these neural networks. The layers are shown here. And this results in 1.8 to 2.5x speed up in these bottleneck operations using the MPU. And MPU is multi-modal, which means that it can execute native neural networks. So in QUETZAL we have object detection using convolutional neural networks, which is a native model, not a replaced approximate model, and MPU is able to accelerate it by some 4x. There are other techniques in paper, including vectorized nearest neighbor search, semantic-aware hardware prefetching for robotics, intra-application cache partitioning, partitioning the cache space for different execution scenarios inside one application, and some engineering optimizations that target contribute to the end-to-end speed up of Tartan, including cache line sizing and optimizing producer-consumer communications, which are frequent in robotics. So altogether, Tartan is able to provide some 1.2x speed up for legacy software, i.e. that is software that is not optimized for Tartan. It doesn't use any of the new instructions. It provides, on average, 1.6x speed up for optimized software while disallowing any approximation when we expect hardware to provide accurate results. And it provides 2.1x speed up when the approximation is allowed. Tartan is open source. It's already available online. Just search CMU Tartan processor. And thank you for your attention, and I'm happy to take any questions.
Please come forward if you have any questions. Yeah, so in the meantime, so I had a question. So your NPUs, are they like inline accelerators? And let's say you said like there is a benefit of like what size of models you can run. Could you add multiple NPUs and make them work together if you want to run some larger models?
That is certainly a possible architecture to have multiple NPU and somehow parallelize the execution of models, different models. But the problem I'm seeing is that we observe in these cases, specifically the approximate cases, the network, the NPU should be tightly integrated with the CPU pipeline. We cannot use NPU as a co-processor because the communication delays will be a problem for these small models. And I believe that integrating multiple NPUs with the pipeline maybe would be costly in some other terms like verification or area or power. But in theory, yes, we definitely can do that.
Right.
So, yeah, I have questions, actually two quick questions. First of all, thank you for the presentation. And just the first question, when we're talking about robotics, I thought it's real-time, right, systems. So, and they're real-time requirements, so you need to process the frame for a limited time. So you cannot just drop the frames, and so that's very important. I think it's one of the important requirements. How do you address this? It's number one. And second question, okay, I'll take a Qualcomm chips, which just goes to a laptop. So why are you better than you, why just your design is better than the existing, let's say, Qualcomm chips? Why I cannot do the same?
Okay, sorry, I couldn't hear you very well, but this first question is about whether the applications are real-time or not, right?
Yes, it's a requirement for robotics that it
Yes.
should be real-time, right? How did you, what do you do with this? So how do you address real-time problem? And the second question, I take a Qualcomm chips,
Yes.
which is just designed for laptops, and just try to use it, I mean, and run this similar benchmark or application and so on. Why I cannot do this? Why your design is better, fits better this? So that's two questions.
Sure,
Thank
great
you.
questions. The answer to the first question is that yes, the applications we have modeled and we utilize for this purpose are applications with real-time requirements. So their performance is ultimately bottlenecked by the computational latency. For example, in the case of Flybot that we have here, let me check whether I have some backup slides. Too many backup slides. Okay, in the case of Flybot, we have a drone operating in the wild, so it performs some photography in the environment. So its end-to-end latency in doing the job, in doing the mission, is bottlenecked by controlling its speed and moving to different locations and perceiving the ball here in this application. And these are time-consuming. Here we have around, on a low-end CPU, we have around 400 milliseconds. So the application does require real-time performance because the computation is the bottleneck, not the mechanical components. So it means that when you accelerate these operations, these 400 milliseconds can be halved, which means that you perform the mission in 2x faster. So I hope I could answer the first question. The second question is that Qualcomm's or any industrial baseline processor we target, the one that we target in this work was Intel Core i7, which also is used heavily for different robots. And we show that we have significant speedups over that. The main contributors to the speedup come from the hardware-software code design. For example, the techniques that we introduce here, like prefetching or oriented vectorization, these are not implemented in any of these processors, and we see that they are frequent in robotics workloads.
Hi, thanks for the talk. Great job. My question is about actually the workload. So I think in Delibot you said that the ray tracing is the problem, and for the Caribot you said that the collision detection was a problem.
Yes.
So I would expect to detect, like, to make the collision detection process, I would also need to be ray casting. So I was like more
Sorry,
about...
could you repeat the last part?
Before I do the collision detection, I would expect to be able to construct a map. So does the map given for that task, or
Yes.
is there... Okay, map is given.
Yes.
Okay,
yes.
thank you.
It's very application dependent. For example, in the case of Caribot, this is the Caribot's end-to-end latency, and perception doesn't contribute much because the map of the factory, this is a robot carrying different objects in a factory, and because the map of the factory doesn't change, it does have the map loaded, so it just performs planning in the map, and all the computation is spent for just making sure that we do not collide with the obstacles in the environment. That is not the case for Delibot, which has to figure out the map online because it is operating in the wild. It doesn't know where it is operating.
Thank you very much.
All right, let's thank the speaker and move on to the next presentation. Okay. So the next presentation is by Deval Shah. She recently earned her PhD degree from the University of British Columbia. Her PhD dissertation focused on energy efficient acceleration for robotics. She currently works at AMD, where she is focusing on AI models and applications. Today she'll be talking about collision prediction for robotics accelerators. Yeah.
Thank you for the introduction. So, autonomous robots are everywhere, including self-driving cars, medical care, home assistants, and so on. These robots perform several tasks such as sensing, perception, planning, and action to achieve autonomy. Recent advancements that are made in the field of AI have provided us very powerful algorithms that can achieve truly autonomous and intelligent robots. However, due to their high computational demand, compute power that is available within certain area, energy, and execution time budget often limits the capabilities of these robots. And that's why it is very important to build compute efficient platforms for these robots so we can make them more autonomous and intelligent. In this work, I am primarily focusing on the planning aspect in robotics. So motion planning is a key task in robotics in which the robot plans how to go from point A to B safely without hurting itself or the surrounding. Typically, more than 90% of the runtime in motion planning is spent on collision detection. So collision detection is heavily used by a planner to determine feasibility of different trajectories that a robot can take to reach its goal position. It is a compute-intensive task with strict real-time requirements. And that's why several ASIC and GPU-based accelerators have been proposed that focus on parallelization, compute and memory-friendly algorithms, and fixed function acceleration. However, we find that in several of these approaches, a significant fraction of the computation is redundant. Collision detection can be easily parallelized, but this naive parallelization comes at the cost of redundant computation. So our goal in this work is to use collision prediction to reduce this kind of redundant computation and achieve compute-efficient real-time collision detection. Now, before going into more details of how we achieve this, I will give some brief background on sampling-based motion planning algorithms. These algorithms are very popular for robots with high degrees of freedom as they are very nicely scalable. It consists of two stages: trajectory sampling and collision detection. Let's take an example of this dot in 2D plane. Now during trajectory sampling, several possible trajectories between the start and goal positions are sampled. Here each trajectory consists of several path segments. Then collision detection is used to determine which of these path segments are colliding so that we can rule out such colliding trajectories and find one feasible one. More recently, several neural motion planners have been proposed that uses neural network for trajectory sampling and collision detection, giving us very powerful sampling-based motion planning algorithms. Now as we see here, during one motion planning run, several of such path segments are checked for collision. In fact, robots with high degrees of freedom, more than thousands of such paths are checked for collision. So let's take a look at one path segment for a robotic arm in physical space. Here, each point corresponds to a position of the robot, and this path segment corresponds to this smooth, short motion of the robotic arm. This motion is checked for collision with the environment by discretizing it into multiple positions, which are further divided into multiple collision detection queries between environment and these robot links. As mentioned before, we can execute these queries in parallel manner, but it also introduces redundant computation. And the key reason behind this is most sampling-based motion planning algorithms require very simple answer. Is this motion safe? So even if we find one colliding query, we can conclude that the motion is not safe. We don't need to execute all these queries. So let's compare different kind of orderings of these collision detection queries. For a naive sequential execution, all these queries are executed one by one, and if we find a collision, we can terminate the execution. In our prior work, we proposed a spatially aware scheduling policy that uses a heuristic to determine the order of these queries such that we can find a collision earlier with fewer queries if there is one. However, if we have a predictor which can predict that which of these queries are more likely to be in collision, then we can prioritize the execution of such kind of queries and find a collision much earlier if there is one. In fact, if we have a predictor with 100% precision and 100% recall, we only need to execute one query here for this motion. Our limit study using an oracle predictor shows that we can reduce collision detection computation by 25 to 40% compared to spatially aware scheduling policy. And this motivates our work on collision prediction. So now let's go through some key design aspects of collision prediction. The first question here is, how do we even perform prediction? Now in a given motion planning run, environmental obstacles are typically assumed fixed, so we can perform collision prediction at the granularity of this link. We can maintain a collision history table which is indexed by the link ID and its position. As we perform collision detection between different links and environment, we can populate this table with the outcomes. And in future, whenever we execute a collision detection query, we can use the link ID and position to access this history table, see whether it was colliding before or not, and determine what will be the outcome. However, now the problem here is during a single motion planning run, these links can assume huge number of different positions, which ultimately gives a very large and sparse collision history table, which is not that useful to make predictions. And to solve this, we take advantage of physical spatial locality. The observation is very simple. Two physically nearby robot body parts are likely to have similar collision output, such as this blue and red link. So based on this, we propose to use a hashing function that maps such physically nearby links to the same entry in collision history table. Now, each entry in this history table maintains counters for how many colliding and non-colliding queries have been encountered so far. Whenever we get a new query, we can read the appropriate entry from history table, use these counter values to determine the probability of this query being in collision. And based on this, we propose CORD, which is our collision prediction approach. Here, for a given link environment collision query, we take the coordinates of the link's center. These Cartesian coordinates are quantized and concatenated to generate the address that we can use to access collision history table. Our collision prediction strategy is also very simple, such that if colliding counter is greater than non-colliding, predict collision. Here we intentionally design the hashing function as well as the prediction strategy to be very simple so that we can keep the overheads of collision prediction to lower level. We show that CORD simple predictor can provide 82% precision with 78% recall for different kind of environmental scenarios and motion planning algorithms. CORD is a prediction approach and it can be integrated with any sort of collision detection execution such as CPU, GPU or ASIC based. We integrate our collision prediction approach with a hardware collision detection unit. So here, a motion environment collision query is given to this link position generation unit, which divides these queries into multiple smaller link environment queries. Now, a collision predictor and a history table together are used to take these queries and make predictions. And depending upon the prediction, these queries are pushed to either of these queues. For example, if a collision is predicted, it is pushed to this queue call, otherwise queue non-call. A query dispatcher reads these queries from both of those queues and schedule it to available collision detection units. Now the query dispatcher is designed in such a way that it prioritizes the queries that are inside this queue call. So even if there is a collision, we can find them early and discard rest of the queries, significantly saving computation. And finally, a result collector and query update unit are used to read the outcomes of these collision detection units and update the collision history table. Our paper discusses each of these blocks and different design aspects in much more detail. Now I will quickly go through the evaluation part. For evaluation, we use very different flavors of motion planning algorithms, such as motion planning network, batch-informed trees, graph neural network-based motion planning. And we evaluated on KUKA and Baxter robotic arm and 2D path planning. Here, we compare the computation for different kind of scheduling approaches across all the benchmarks. Here, as shown in the figure, compared to spatially aware scheduler, CORD predictor provides 17 to 32% reduction in the collision detection computation. CORD is a very simple, lightweight predictor that can achieve performance very close to the Oracle predictor. To summarize the evaluation, CORD predictor reduces computation by 17 to 32%. We show that it can improve performance per watt of these collision detection hardware accelerators by 1.23 times. We also show that collision prediction provides higher improvements for more difficult and time-consuming motion planning queries, such as going through narrow passages. In the paper, we discuss several aspects in more detail, such as different hashing functions, collision prediction strategies, collision history table update strategies, how does these design aspects affect precision, recall, energy efficiency, and computation reduction. And finally, collision prediction evaluation for CPU and GPU-based collision detection. Our code is also available, and with this, I will conclude my talk. I'm happy to take any questions. Thank you.
Are there any questions?
Hi, you have commented that the strategy to updating the collision history is on the paper, but could you talk a little bit about that? Because from what I have like thinking during the presentation. If you update when you make a prediction, like there is no, like if you predict a collision and you update the table saying that, okay, there is a collision, you always are going to predict that a collision will happen. But if you make a prediction and also compute if there is or no a collision, like there is not much gain in predicting. So like when do you update the table?
That's a very great question. In fact, we see like how we make predictions here also affect how we design the collision prediction strategies. So for answering your first question, we don't have one single collision detection unit. In the hardware, we have multiple collision detection units. So even if you prioritize entries that are in this queue call, there is a good mix of queries scheduled to the CDUs that are colliding and non-colliding. So it is not like we are always updating the table with outcome of colliding queries. There are also non-colliding queries. Definitely there is a bias that colliding queries are used to update the table more than non-colliding, but it is also works in favor of us because we basically want to predict colliding, whether it is colliding or not. So history about colliding queries is much more useful than non-colliding.
I think there was a question there. Okay.
The collision history table is in software, right?
So it can be implemented in software or hardware. So for CPU and CPU and GPU based implementation, we implement it in software. But for ASIC based implementation, we implement it using SRAM.
Okay. I was going to ask that if the planning algorithm is parallel, the multiple threads could access this history table. And in those cases, we need the locks, for example, to ensure that operations are safe. I was going to ask, in those cases where everything runs on CPU or GPU, is there any point in implementing this table in hardware in order to avoid those overheads if the overheads are high? And are the overheads high? Overheads of accessing and updating this table?
So I believe that here there is no wrong or right. So it is okay if you read and not updated entry, if you read an old entry, because here you are making a prediction. We are not affecting the execution correctness in any way. So we can get rid of these overheads of log, and we can. Yeah.
Thank you.
Hi, Rahul here from ETH. So excellent talk. So I have one question. In the collision predictor probably has some accuracy issues also, right? So can you comment on the downsides of the accuracy? Like, have you seen the possibility that a query that actually ends up predicting that it's not going to collide, but it actually gets to collide? So it gets actively deprioritized. Have you seen any overhead for that the deprioritization?
If you make a wrong prediction, then you will be end up doing same execution, like same computation as the baseline. Because we are not letting it affect the execution correctness. Whatever entries are predicted and are in queue call, we will execute them first. So if we make wrong prediction for one or two queries and put them in queue non-call, still there is a good probability that at least one colliding query will be in queue call. So we don't need 100% precision here or 100% recall here. We can achieve very similar computation reduction compared to Oracle with less precision and recall.
So it means that even if the predictor is wrong, it just reduces the opportunity to...
Exactly.
Input. Okay,
Yeah.
perfect. Thanks.
Yeah. Thank you.
There's a question here, but meanwhile, just like a follow-up on that. So what if you don't get anything in your queue call? Have you compared against like doing a random distribution of these positions into the queue call and non-call, and how do you compare against them?
So in our prior work, where we proposed spatially aware scheduling policy, there we compared with random, and spatially aware policy already performs much better than random. we build prediction on top of spatially aware scheduler. So if you don't get any useful prediction, you will still get benefits compared similar as spatially aware scheduling.
Okay. Thanks. Okay. Maybe you can get that offline, but let's move on to the next talk. Let's thank the previous speaker. Yeah. Okay. The next speaker is Singhi Han. He's a PhD candidate at KAIST, South Korea. His research interests are in efficient architecture for emerging applications and hardware-software co-design for end-to-end systems. He's going to present today on one of the most emerging applications on DNA sequencing. So let's welcome the speaker.
Hello, I'm Singhyun from KAIST, South Korea. Today, I will introduce about our paper, Less Bandwidth and Locality Enhanced SMEM sequencing acceleration for DNA sequencing. Before we start, I will briefly introduce what DNA sequencing is. DNA sequencing is a technology that determines the order of nucleotide base pairs. It has a critical role in identifying mutations related to genetic disorders or disease, and its importance has increased immensely with the occurrence of COVID-19. It's okay. Okay.
Yes.
Yeah.
Sorry.
It's okay.
Sorry about that.
Okay, thank you. Sorry for inconvenience. Okay, I'll continue my presentation. But unfortunately, DNA cannot be read at once for analysis. So in next generation sequencing, or NGS, it tries to first analyze small DNA fragments and then combine them for more information. So these small DNA fragments here are called short reads. We have to align these short reads with certain conditions to get the reference DNA. But this process is called read alignment, and this aligning process is the most time-consuming task in NGS, accounting for up to 80% of the total process. In read alignment, short reads are arranged based on the reference genome. This process consists of two steps, seeding and seed extension. In seeding, each part of the short read is compared with all locations of the reference genome. This comparison is repeated for every short read, and the matching results are called super maximal exact match, or SMEM. Then, the seed extension is conducted, in which SMEMs are extended on each side. Then they are merged together. Analyzing the minor differences between the reference genome and our new aligned sequence it can explain the given DNA-related phenomena. Here, lots of memory comparisons occur during the seeding process for comparisons. As you can see in the previous example, since seeding requires numerous memory accesses, it remains an open challenge due to its memory-intensive characteristic. The simplest seeding method is to compare two sequences one by one. However, this is very inefficient. Thus, an index data structure is required to simplify the search process. Index data structure is a structure that stores the relationship between reference sequence and any possible sequences. It is usually used with suffix array for efficient search. As shown here, suffix array is another data structure that saves sorted suffixes and its index of given reference sequence. An approach known as learned index has emerged as a new index data structure to assist the search process. Learned index is a machine learning model-based structure that saves the guaranteed range of search rate location in the suffix array. For example, to find sequence CA in the suffix array of reference sequence ATGCA, learned index helps us to get a range where CA exists. From the given range, we need to perform a binary search. Therefore, the complexity of algorithm is bigger of log of given range, and using the learned index is much more memory friendly compared to the conventional algorithm because complexity does not increase proportionally to the sequence length. Here is process of seeding with the learned index data structure. First, the part of short read we want to look for in reference DNA is used as key for the learned index model. Then, learned index model gives the expected range of positions in the suffix array. In the suffix array domain, two searches are conducted to find the SMEMs. First, binary search is performed to find position where the short read and reference DNA matches the longest. These positions are called longest exact match position, in short, LEM position. Then, exponential search is performed to find every positions in the same match length in the suffix array. These matches are considered to be SMEMs. During each search iteration, we have to get the address where the reference sequence we are looking for exists, which is in the suffix array memory. Based on the decoded address, reference sequence from the reference DNA memory is assessed for comparison. Therefore, two external memory accesses are occurred for every iteration. After short read and fetched reference DNA are compared to find match lengths, after the exponential search, SMEM search result is used for the next search process. Oops. In learned index-based seeding, we make three key observations. First, learned index data structure requires a dedicated hardware design. Current seeding algorithm shows low data utilization, and previous work suffer from large index size. So, for high performance, suitable data structure and seeding-specific data flow is required to design an efficient seeding system with faster memory. Second, there is a lack of locality in the memory accesses. However, we find that opportunities for spatial and temporal locality exist in the search process. Last, randomness at runtime. Each memory accesses are random at runtime, and execution time of each workloads are diverse. To resolve these observations, here is a summary of the contributions made by Bless. First, we propose a new data structure named coarse-fine block data structure. It reduces the memory access during the search by exploring spatial locality and improving memory utilization. Second, we propose a new algorithm named guaranteed search range update. This algorithm reduces the memory access during the search using temporal locality and caching. Lastly, we propose an end-to-end seeding accelerator architecture. It can leverage multiple seeding cores and HBM memory and consists of a runtime scheduler to load balance between multiple cores. Now, I will introduce these key features in details. First is the coarse-fine block data structure. In coarse-fine block data structure, we divide suffix array indexes into two groups with hyperparameter interval. First is coarse index, is an index at the multiple of interval, and other is fine index, which is the index between two coarse indexes. This coarse index is saved alone in the memory line, along with the partial copy of reference DNA where the coarse index points to. Since two related memories are located in the adjacent memory, special locality is enhanced. Meanwhile, fine indexes are saved together with its adjacent indexes in the same memory line for additional special locality. By doing this, we increase the effective bandwidth of memory. Through this data structure, special locality between suffix array and reference DNA can be utilized. Conventionally, after accessing a suffix array, additional access to the reference DNA was required. So this would be the time taken for one comparison. But with CF block structure, only one access is required. So the 50% of memory access can be saved with CF block data structure. Also, special locality between suffix arrays can be utilized. Conventionally, after one iteration of suffix array and reference DNA access, another iteration was required. So this would be the time taken for two comparisons. But with CF block structure, after one iteration, suffix array access can be skipped and only reference DNA access is required. So maximum of 75% of memory accesses can be saved. Next, we developed the GSLU algorithm. During multiple searches, there are overlapping search area which can take advantage of temporal locality. However, storing every search result is not hardware friendly. So by tracking the search reason during binary search, GSLU algorithm finds unnecessary search reasons during the exponential search to reduce memory accesses. In GSLU, there are 4 pointers. These same pointers point to the furthest position from alien position, which has longest match length, and gdiff pointers point to nearest position from alien position, which has match length shorter than the longest one. These pointers are updated at every iteration. Below is an example of the GSLU algorithm. Assume that during the previous binary search, shown colored positions are already known and cached in the memory. Then assuming 15 is the longest match length, which is alien position, GSAM pointers will be updated like this, and since 9 and 7 are smaller than 15, the gdiff pointers will be updated like this. The positions outside the gdiff pointers are already known not to be included in the results, and the positions between GSAM pointers are already known to be included in the results of which is SMEM. So only 2 positions between gdiff and GSAM pointers are unknown, and they are needed to be searched. So comparing with conventional search area, this area is very small, which means memory accesses can be reduced. Now I will introduce our hardware architecture. BLAST consists of the seeding core, core scheduler, crossbar network, memory interface, and HBM memories. Seeding core performs the seeding operation, and core scheduler schedules and controls the seeding cores and manages the host communication. Seeding cores are connected to memory interfaces with the crossbar network, and every memory interfaces are connected to each channel of HBM memory for memory-related operation. In details, seeding core consists of the feeder, search controller, and search engine. Feeder saves search reads temporarily and issues them to the search engine. Search controller manages the search process, and the search engine performs the actual SMEM seeding operation. Here, the number of running workloads is maintained by assigning OIDs to each process. To handle runtime variation, the core scheduler redistributes the workload for load balancing. Every cores are assigned the same amount of workloads at first, and then the cores that finish their given workload take the workload from other cores that are still learning based on a round-robin policy. In the given example, after core 0 finishes its given 10 workloads, it takes the workload from core 1, which is still learning, the workload 16. The operation is repeated until every core finishes its given task. Lastly, memory interface utilizes CAM for core address saving and has inter-channel movement of data. For more detailed hardware architecture, please refer to our paper. Now, let's look at the evaluation. Evaluation is conducted with cycle accurate simulator based on C++, which operates with Ramulator for accurate memory consideration. First, we conduct the design specs exploration to make a design choice. Based on the result, we find the optimal of hyperparameter interval is 16. Also, we see that BLAST saturates its performance at 16 cores and 64 OIDs. To evaluate the performance of our system, we use human genome reference for reference DNA and human genome benchmark dataset from Illumina for short reads. Also, as a baseline, we compared our system with BWA MEM introduced on Bioinformatics 2022 and ERT introduced on ISCA 2019. The speed of seeding is how fast the system can perform read matching, so the performance indicator is reads per second. Our baseline of scaled-up HBM-based system architecture achieves 56 million reads per second. Then the addition of CF block data structure achieves 2.05 times speedup, and GSL algorithm achieves 1.09 times speedup by utilizing spatial and temporal locality respectively. Lastly, our runtime scheduler achieves additional 1.11 times speedup, thus our overall throughput is 135 million reads per second. Also, our runtime core scheduler works well, showing 11% lower execution time on average and up to 62% lower execution time in the worst case. This is area and power analysis of our system, synthesized in TSMC 28 nanometer technology. Analyzing area, FIFOs in the seeding core and HBM PIs account for the largest area. Compared to the previous work, we achieved 10 times higher performance per area and 12 times higher performance per power. In conclusion, we propose a corresponding block data structure and guarantee search range update algorithm to utilize locality and achieve higher bandwidth utilization. Also, we propose a seeding accelerator architecture with HBM, specialized data flow, and a runtime core scheduler. As a result, our system shows up to 36 times faster performance, 10 times higher area efficiency, and 12 times higher power efficiency compared to the previous state-of-the-art systems. Thank you for listening. If you like this talk, please look at our paper for more details, and I'm happy to hear any questions. Thank you.
Are there any questions? I just had one question. Mm-hmm. So you said in your scheduler you were looking at it more from a time balancing to put it on the different cores.
Yes.
But because you're also caching, did you consider how much active data you have across the cores to then schedule your tasks?
The caching occurs between each workloads, and our load balancing occurs between the caching occurs between each step of search in one workload, and the load balance between cores occurs in domain of processes. So yeah. It does not there's no
interference of
no
one
interfaces
workload
of one workload to the other. Every workers are not they don't have any
they don't evict out data from the other cores. Okay, all right. Yeah, there's a question here.
Thanks for the presentation. Nico here from ETH. So my question is that the speed up that you reported, were they for the seeding step or for the end-to-end read mapping step? And if for the first one, do you have ideas about the second one and vice versa?
Pardon?
So basically, the speed up you reported, was it for the seeding step or end-to-end read mapping step?
Oh, my speed up is based on seeding step only. So
do you have ideas how the end-to-end read mapping process would be accelerated?
We couldn't attach our accelerator to the seed extension accelerator, but in read alignment, seed extension is also important as the seeding. So we couldn't do the experiment. But seeding is also one of the most time-consuming tasks in end-to-end system. So I think it's enough to.
Yeah, definitely. Thanks.
You.
There's one question over there.
Thank you for your talk. I have two questions. Okay, both are about the comparison evaluation part. Mm-hmm. So the first question is that your comparison baseline ERA, right? although it's an ASIC, but somehow it shows only like 3 times performance gain over the CPU-based BWMM. So do you have any comments on this part? And also, like your gain or your final result shows that your performance per watt and per area is much larger than the ERA. And do you have any like comments of like what makes this result?
First, for the second question.
The second question is that your result shows that your performance per watt and your performance per area is much larger than the ERA. So is there any or any reason for this performance gain?
We thought that there are 2 reasons for speed up. First is we used HBM system, which has much more higher bandwidth, but compared to the ERT, which used the DDR-based system. So first reason is HBM has much more higher bandwidth compared to their area or power efficiency. That's the first reason. And secondly, our system's memory, we used like new data structure to increase our memory utilization. So the effective bandwidth of our system is better than ERT. So I think there are 2 reasons for your second question. And can you repeat your first question, please? I'm sorry.
The first question is like I'm curious about like why the ASIC the performance result of ASIC is only about like 3 times of the CPU-based BWMM. So yeah, so what is the reason for this?
As you can see, our ASIC system is 36 times faster than CPU system.
I mean the ASIC, the ERT. Sorry.
ERT.
Yeah.
What are the drawbacks of ERT that wasn't as good?
Only 3 times over the second bar, the BWMM.
I think the reason why ERT shows only 3 times is ERT's basic algorithm is the BWMM2. You can see at the 1.07.
Yes.
But the BWMM, you can see in the second line, is based on the learned index data structure. So 2 CPU baseline systems are using different data structure, and the 3 times faster shown in the BWMM, like comparing to the BWMM2, is come from the different data structure. But ERT is based on the first CPU-based system, so it shows 8 times faster than the CPU system. Okay. But after then, the learned index data structure was introduced.
Okay, I see. Thank you.
Thank you so much.
I think let's thank the speaker again, and we'll move on to the next speaker. So the next speaker is Julian Pavon. He's a final year PhD candidate at Universitat Politècnica de Catalunya with contributions at ISCA and HPCA. His strong focus has been on solving complex problems related to irregular memory accesses for vector processors. And he has already submitted 2 patents in this domain. So let's begin the talk. He's also talking about how can you use vector acceleration for genome sequencing.
Thank you for the introduction. Okay, I want to start my talk with a fun fact about this paper. Like the initial team of this paper, we were all Mexicans. Then we select the name QUETZAL because of the importance for our culture. Okay, then. Now, to start with the technical part, I want to talk about the pipeline of the genome sequence analysis that goes all the way from the sample to find those characteristics in the DNA that says why we were sick or why we have more we have more danger from certain illnesses than others. Then the main focus of our work or the motivation comes from the sequencing and the read mapping. Sequencing is taking the blood sample and converting it into data that can actually be processed by a computer, and read mapping is, in this case, processing this data. No? Something that we can say about sequencing is that year by year it's becoming more cheaper, and is, like in this case, cheaper, and it's becoming more affordable. On the other side, read mapping is becoming more and more compute intensive, going from short reads to long reads. Then this brings the first requirement, that is, we need to support both long and short sequences in our system. Read mapping consists of 3 main steps that they are going to go from indexing, filtering, and alignment, bringing the second requirement to our system, that is, we need to be able or flexible enough to map multiple algorithms into the same hardware. The 2 candidates that we were analyzing are general purpose hardware and accelerators. On the one hand, general purpose hardware, they are really flexible, but they are limited in performance because of this flexibility. On the other hand, accelerators are really efficient and high performance, but they are generally tied to a single algorithm or to single input data. Then we raise the question, is it possible to meet in the middle, like something that is flexible enough to be mapped to multiple algorithms, but at the same time fast enough to provide like significant performance benefits? And the answer to this is QUETZAL, our hardware-software co-design vector acceleration that addresses all the bottlenecks from vector architectures for modern genome sequence analysis, providing high performance benefits while being really flexible to be mapped to multiple algorithms. Then the key contribution of QUETZAL is first, as I mentioned, we are addressing the bottlenecks from genome sequence analysis on vector architectures. Then a CPU with QUETZAL features a 5.7x better performance than the baseline CPU, and when processing long reads, QUETZAL cannot perform to GPUs. Then, set this introduction, let me go with the background of our work. Let's start first talking about algorithms. When we talk about genome sequence analysis, we know that alignment is processed by a DP, like dynamic programming, where we have a dynamic matrix that needs to be filled. On classical approaches, we need to calculate all the cells inside of the matrix. Modern approaches only compute those cells that belong to the optimal path in the alignment, reducing a lot the computation. Then these algorithms features high data level parallelism that we selected to approach it with vector architectures which follow the SIMD, single instruction multiple data taxonomy. Now, how they work and why are they so efficient for DLP? Then, an example, when we compute on a scalar core, we take every element from memory, process them, and generate a single result that will be used or stored back to memory. On vector computers, we get streams of data, compute on all these streams at the same time, and generate multiple results in a single instruction. That's why they are so efficient when processing DLP. However, modern genome sequence analysis algorithms have bottlenecks that stop them to fully exploit the benefits of vector architectures. Then, let's do this more practical to show you what are these bottlenecks. When we want to process, in this case, the wave-from-align algorithm, we start with the input sequences that they will be in memory. We need to gather them into the vector register. This process of gather actually is, every instruction takes at least 22 cycles if the data is already in the L1. If data is not in L1, this latency will drastically increase. Then we can observe a first bottleneck here. We have high latency to go for the data in memory. After getting the values, we need to process them to find the maximum number of contiguous matches in these input sequences. However, as you know, many of the frameworks on genome sequencing analysis use bit encoding data to reduce the overhead, the memory overhead of the input sequences. This is translated to a set of chain instructions that they are required to handle this bit encoded data. Finally, I need to check if I found all the matches or if I should continue iterating on this process. Then we have 2 bottlenecks: the scatter-gather instruction with really high latency and a big number of instructions in the body of the loop. How this translates to the performance then? We can observe that most of the execution time is actually wasted on waiting for the reservation station because of the high number of instructions and waiting for the catches because of the high latency of the scatter-gather instructions. Then, here is where we said, okay, how can we address this? Then QUETZAL actually takes down these bottlenecks by reducing the latency of scatter-gather instructions and reducing the number of instructions in the body of the loop. Now, all this said, let's talk about a little QUETZAL, no? QUETZAL is a hardware software co-designed vector accelerator that is tightly coupled to the vector hardware path in the CPU. Then we are reusing the components of the CPU to reduce the overhead of QUETZAL, to not put more units in the CPU, but actually improve the utilization of this hardware. How does it work? First, QUETZAL supports bit-encoded operations without extra instructions. Then that was one of the main bottlenecks that I showed you. Next, it reduces the latency to get the values for the input sequences from 22 cycles to only 2 cycles. That's a 10x better latency than the normal implementation. And finally, it has a specific ALU that it gets these input sequences from the buffers and calculates the maximum number of consecutive matches in the input sequences, reducing the number of instructions, addressing both bottlenecks that we mentioned at the beginning. But how will this be looking in the algorithm or in the execution? Then, we start with the same input sequences, but now, instead of using a scatter-gather instruction, we use efficient unit stride loads to place these input sequences into our buffers, into the QUETZAL buffers. Then, for the next step, we are going to use a new QUETZAL instruction that is QUETZAL read to gather the values from the buffers and place them in the vector register file. We execute to calculate the maximum number of consecutive matches using the count ALU, and the rest of the process is the same. We need to check if we finish or if we need to continue iterating. Then you can see, in this case, I reduced the 22 cycle latency per read to only 2 cycles. And now, instead of having a really big number of instructions, I only have a single instruction in the body of the loop. Then, in this case, QUETZAL is addressing both bottlenecks that stop genome sequence analysis algorithms to exploit the benefits of vector computing. But how does this look in performance? This sounds really nice, but actually, how much is the benefit? Okay, let's go there. First, to evaluate sorry. Great, thank you. Then, to evaluate QUETZAL, we use Gen5 to model a 60-core, where each core features a QUETZAL engine. And we run an Ubuntu 20 operating system. All the results that you will observe for this plot are normalized to the baseline CPU. Then, I start saying we need to have a really flexible machine. Then, to show that QUETZAL it has the flexibility that we require, we had a really extensive methodology. First, we evaluate 5 different algorithms, 3 modern algorithms, 2 classicals. Next, we use more than one alphabet, DNA and proteins. Third, we are analyzing short and long sequences, another requirement that I told you at the beginning. And finally, we evaluate 2 different QUETZAL implementations, one implementation featuring only the buffers, and another implementation which includes buffers plus the count ALU, because in this case, based on the requirements of your application, something that can be done is that if you do not need the count ALU, you can apply clock gating to reduce the energy overhead of this hardware. Okay, then, first of all, QUETZAL outperforms all the evaluated algorithms, providing a 5.7 better performance compared to the baseline CPU. And it accelerates both modern and classical genome sequence analysis algorithm. We didn't stop there with analysis. Actually, we also evaluate QUETZAL compared to another general purpose hardware that is GPUs on one modern and one classical algorithm for both short and long DNA sequences. And we compare, in this case, our QUETZAL CPU with an NVIDIA A40 GPU. we can observe that for long sequences, QUETZAL features 2.7x better performance and 1.1 better performance for the modern and the classical algorithm evaluated. Then, as the importance of long sequences is continuously increasing, QUETZAL actually is providing a platform that can be useful not only to accelerate these algorithms, but actually to continue growing with the new algorithms that are going to be proposed. Finally, we evaluate the area overhead of QUETZAL using the Synopsys ICC2 place and route tool, targeting the 7 nanometer technology and a 2 gigahertz frequency. We show that all the benefits that I just told you, that nice 5.7%, X better performance, and all the performance against the GPU is only with the cost of 1.4% of extra area overhead. That means that with the minimum changes and better using the hardware available in the CPU, we can actually get really significant performance benefits. Other content in the paper that you can find is, for example, we run a detailed design space exploration to right-size the buffers in QUETZAL, and also we had a comparison with ASIC accelerators, and we didn't stop in genomics. Actually, we also run 2 extra kernels that are sparse matrix vector and histograms, where actually also QUETZAL outperformed the baseline CPU. To conclude, we realized that when you are trying to accelerate the genome sequence align pipeline, you need not only performance, you also need flexibility. The vector architectures in the CPU are really attractive because these algorithms has a lot of data level parallelism, but as we show, they also feature, these algorithms have a specific bottleneck that stop them to fully exploit the performance and energy efficiency from vector architectures. To overcome this, we designed QUETZAL, a hardware-software co-design genome sequencing accelerator that features 5.7 better performance than the baseline CPU, and as you observe, it can get up to 2.7x better performance than GPUs when processing long input sequences. That will be all for me. I'm open to any question, and thank you so much.
This is great work. So I can definitely see how maybe like optimizing index axes would help with irregular algorithms like WFA. But for something like Smith-Waterman, right, which has more regular axes, can you talk more about where the benefit is coming from Smith-Waterman? Are you able to use those Q buffer optimizations for Smith-Waterman, and if so, how?
Yeah, for Smith-Waterman, what we were doing is that when you are using vector computing in the implementation that we were using from the KS2W, it was happening that you were placing data in the memory, and then you need to read a segment of that data, but as the load, in this case, the load store unit do not do any coalescing, actually you need to store and load the data again, doing a lot of store load forwarding. What we do is that we place this data and we shuffle it in the buffers, like to avoid going to memory and do all the things between the buffers and the vector ALU. But as you mentioned, the main bottleneck on these algorithms is not the index accesses. Then that's why it's not. As in this case, for wavefront aligned, you can observe that we get tremendous performance benefit because they are dominated by index matching. Meanwhile, on the classical, we get good performance benefit of 1.3, 1.4x, but it's more limited to the reduction of the load store forwarding. Thank you so much for your question.
Any other questions? All right, maybe one last question and then we can end this session. So I saw that you are using some of these like merge Q buffers to be able to do the gather operation. So how does this technique compare to some of these others? Like, because you said you also did this on sparse matrix multiplication. So how does it compare to some of these other existing architectures that have specifically been proposed for this sort of a gather?
Okay, thank you. Actually, this is a nice question. Something that we do with QUETZAL when we say that we are doing hardware software co-design is that we analyze carefully the software to propose a solution that can actually be beneficial for the software by the definition of the software. Then for sparse algebra, there are a lot of techniques that they improve the locality of the memory accesses by applying, for example, matrix blocking that actually reduces the size of the memory that you need to traverse. This helps to us because now we can place this segment of memory into the QUETZAL buffers, and we can do all the gather scatter to maximum speed into the buffers. Then the idea of QUETZAL is that if there is software around, like in this case, it improves locality, but this locality is input dependent, it still relies on gather scatter, scatter gather, then we can actually provide them the hardware that they need to actually exploit this locality.
Right. Okay. Let's thank the speaker, and that will be the end of this session. All right. Thank you, everyone.